This is kind of an overview of a series of work that's been going for a while. So if you've heard me give a talk in the last year, I'm sorry, but the first few slides will be repetition. But for everyone else, it'll be hopefully good background. And this really targets a specific problem that's, I would say, of crucial importance to some architectures and maybe not so important for others. But at Google, we are building 2D nearest neighbor superconducting qubit chips. And so we're building a square lattice and targeting the surface code. These are ideas I'm not going to introduce. You've heard them a few times in the last few days. But as we sort of start to build these things, there's a lot of experimental realities that we have to contend with. And one of the ones that we're going to highlight here is component dropout. So far, every QEC experiment that you've seen from any presenter here or in the field at all has kind of been run in kind of a NISQ way, where shots are very cheap, systems are somewhat cheap, and that like we are willing to fabricate multiple devices to get the one that we want to run things on. And we don't really need to worry about scale in the same way that we will in a few years. But as we start building larger and larger systems, things like a single broken qubit or coupler won't be a reasonable excuse for throwing that chip away and starting again from scratch. And so we need to find out how to handle these things and adapt all of the beautiful error correction theory that we know into this sort of grungy reality of the chips that we actually can make in the near future. Maybe in 30 years, we're not worried about this. But for right now, this is just the reality that we have. There are broken qubits, couplers. There are also, in our systems, two-level systems and things where maybe a qubit isn't broken, but for whatever reason, right now, it's just not very usable. We have widely varying error rates and so on. And so we'd love to be able to deal with this in some way. And then on the left here, I have just an example of a few unique cases: broken data qubits, broken measure qubits, different orientations, and so on. And so to do this, I'm going to go through first a little bit of background. I'll then explain this method called LUCI that we developed a few years ago that handles this problem. And then what I'm hoping to do is get to a few interesting improvements at the end. We have had a few more papers come out in the last 6 months or so. And so I'd like to talk about some of the improvements to this framework, as well as maybe a bit of a last-minute tie-in to the sort of topic of this conference and how we can use this to bridge towards NISQ. So to start, we have the surface code on the left, bottom left here. And so, this is the regular surface code that we all know and love. And this on the top is sort of a cartoon for the reset layers, and then the 4 layers of CNOTs that make up the usual surface code circuit. And this paper on the bottom left from McEwen, Bacon, Gidney showed that halfway through the CNOT layer setup, you could have you have an unrotated surface code state on both the data and the measure qubits. So now the qubits that lived here had a Z reset, and then 2 CNOT layers have propagated that to a weight 4. And then this weight 5 is propagated to this weight 3, and so on. And so you have twice as many stabilizers here as you do on the left or right. And you are occupying twice as many qubits. And the interesting thing they found in that paper was that you actually could think about surface code circuits not as measuring these end cycle stabilizers, but as measuring these mid-cycle stabilizers and then re-preparing them. And so you can basically derive almost an identical circuit to the usual surface code circuit by instead thinking about measuring diagonals of this mid-cycle state, re-preparing them, and then measuring the opposite diagonals in the next round. And then they use this intuition to find a number of interesting circuits. So prior to 2023, we would have said there's one good surface code circuit. This paper introduced 3 more. They showed a circuit that exists on a hexagon lattice instead of a square lattice. They showed a circuit that uses CNOT swap gates, or I swap gates, instead of CNOTs. And they showed one that actually walks around that Bill talked about a few days ago, a surface code that drifts through the patch as it sort of does its QEC cycles. And so LUCI introduces, and I should mention that actually a paper from last week from Austin, who spoke yesterday, also introduces a new interesting surface code circuit as well. So there are other ones that we're now starting to find. But LUCI really is an infinite family of surface code-like circuits. There's some debate on what exactly makes a circuit a surface code circuit versus just surface code-esque. But they will have surface code boundaries, at least. They'll have all the logical operations we want. But it's very flexible. And specifically, we're going to use that flexibility to find instances that do not need a certain qubit or coupler that we don't have access to. And I'll show you a few processes for how we actually can get there. So to do that, I'm going to spend some time in this slide. We developed this sort of graphical language called a LUCI diagram. The name LUCI comes from, well, it comes from me wanting to make a pun in the title. But the justification is the shapes are L's, U's, C's, and then there's also weight 2 I shapes that can come up. And so what happens in these diagrams is the backing checkerboard is the mid-cycle state of the circuit that we're going to generate. We use that as kind of the landmark state that we return to. And then these different shapes tell you how we're going to measure a given mid-cycle stabilizer in that round. So for example, here, I'm going to measure this weight for ZZZZ operator and then re-prepare it. I'm going to do that using a sort of small CNOT ladder, a measurement, and then reset, and then generate it back out again. And in the process of doing that, I'm also going to be moving these other stabilizers that aren't being measured in that round. And for example, this Z stabilizer will propagate somewhere, hit this measurement, and then propagate back to where it was before. And so every detector, which is formed by 2 measurements, will be formed first by one measurement sort of in the middle when it's not being measured out. And then subsequently, that shape will be measured out fully, and that'll form your detector. And I'll go over that in more detail later on. And then to finish reading these diagrams, the dots on each shape indicates which qubit is actually going to be measured in that round. And the colorings go from light gray to dark gray to black. So you can kind of see here on the right, hopefully this is visible, there's kind of a gradient to indicate where information is flowing to and from. So this is kind of the language I'll describe these circuits in. And the promise that I'm going to make is that you can translate this directly into a circuit, into detectors, in a very well-defined way, and that this can all be done in code. So you can just make these things, and I'll show you later it gets really complicated, but the code can handle all of it automatically, and you don't have to really deal with that muck. There are some rules. Yeah.
Just okay, I'm trying to.
Yeah, this is a good slide to ask some questions on for sure.
So I'm just looking at the difference between like the on these like LUCI to standard surface code to back to LUCI.
Yeah.
So should we think of it in the first case? It's like these are the stabilizers if you include the ancillas.
Right. Yeah. So if I include the ancillas, there's actually a more involved figure that is in the original paper. But if you include the ancilla, so right after this reset round, for example, I'll reset this qubit in the middle in the X basis. And then this weight 4, you should think of as kind of propagating to a weight 5, where you include that reset in as well. It forms what they call the flag state that looks kind of like this. And then you'll also introduce a weight 1 stabilizer just on that reset. So you now have a weight 5 and a weight 1. And then the CNOT layers that kind of follow will propagate that weight 1 into another weight 4, possibly this one, depending on the particular choices you're making. And then the weight 5 will propagate into the other one. So what ends up happening is you'll measure out half of your X-type mid-cycle stabilizers in a given round, and the other half are the ones that are kind of being stretched out and opened back up again. And that's kind of the sort of life cycle of these things. And this also happens in the regular surface code circuit. We're looking at it from a sort of pi out of phase picture, but this is what's happening in the regular surface code circuit as well, is that your measurements, you're going to say, oh, my detector is comparing these 2 measurements, but the detecting region that catches all the errors that thing sees actually starts with the reset 1 round earlier. So it starts at a reset, propagates out to your stabilizer, hits that measurement, and then closes back up again, and then hits that second measurement.
So could you say then you're reinterpreting which stabilizer measurement is being measured?
Yeah, you're looking at this
earlier in time.
Exactly. These things are really 3-dimensional or 2 + 1 dimensional volumes, where you can think of error correction. Now, I'll talk about this at the end. You really could think about error correction, and like we would sell you on thinking about it this way, as a 2 + 1 dimensional space-time tiling, or more than 2 dimensions if you so choose. And these volumes are really the fundamental thing. And the stabilizers that we all talk about are just the cross sections right after the measurement round. And you can instead think about them in this cross section, and it's all still well defined. Logical operators are really sheets that go through your entire space-time, as Austin was talking yesterday. And we tend to define them at this point in time, but you can just as well define them anywhere else, and they'll still propagate the same way. So that's kind of the overall picture that I'm trying to sell. So there are some rules to how these things fit together. I won't get into too much detail, but basically, this corresponds directly to a circuit, and so does this. And qubits are on these nodes. So the C0 layer, the C0 gate that's defined by this, better be the same C0 gate that's defined over here. And if it wasn't, then there would be collision. You couldn't put those two shapes together. Similarly, in this case, you would again have some gate collisions. And so essentially, you're constrained to follow this snake-like pattern, where you have a U and then an upside-down U, and then a U and an upside-down U, and so on. And this kind of is how the regular surface code circuit looks. This is how the three-coupler surface code circuit will look. You'll just have these columns that are filled in with these snakes. Again, I'm not going to get into too much detail in the hopes of getting to the final parts of my talk. But there are rules to this. It's not just insanity, but the rules are still pretty flexible. Yeah.
So how many bits do you get out of this? How many more bits? Because normally we'd think it's just you get d squared bits essentially out of like one round, right? And
so you get the same number of bits as before of information extracted. You'll notice that I'm measuring half my stabilizers on average in a given round. So each of these individual boards is one round. And so I'm measuring, like, in this round, I'm measuring this guy. In the next round, I'm not measuring that one. I'm measuring this one, and so on. And what you can see is that, so this is for I should mention, this is for a three-coupler surface code circuit. So you can see, like, this 2-qubit gate is not used in this round, and it's not used here. So you actually wouldn't need that coupler in this chip. And in the three-coupler surface code, you have this interesting behavior where the measured qubits alternate the basis they're measured in. So this particular qubit is measured in the z basis in this round, reset in the z basis, propagates out, and then this round is measured in the x basis. But you're still measuring, in this particular case, the canonical measured qubits of your chip, and you are extracting the d squared.
Okay, so the notion of the additional stabilizers is just the notion of what state the code is in.
Exactly. It's just because we're not thinking about it after the measurement. After the measurement, for a moment, those d squared qubits are removed from the code space, right? Here, because I'm looking at it at a different point in time, I need to think about the stabilizers that started out from the previous round and the stabilizers that are closing up. If you look at it right from measurement, you don't think about the measured qubits as being part of the code at all.
Okay, so you're not measuring all the stabilizers then
in every round. No, I'm measuring half of them.
Not in every round, but total, right?
Over the course of 2 rounds, I'm measuring all of them.
All the ones in the middle, all the ones in the standard ones, but not
yes.
the new ones. Okay.
Yeah, exactly. All the ones in the standard surface code are being measured every round, which corresponds to half the mid-cycle ones being measured every round. There are twice as many stabilizers as there should be, in a sense. All right, so there's some rules to this. And then I'm going to show you quickly a procedure for generating one of these things. I'm then going to show you improvements to it. So if there are, I will take questions, because actually time isn't going so horribly. But I might table some questions if it's about a point that I know I'm going to improve in a few slides. But feel free to ask any questions you have on this process. So we're going to start with some distance. I believe it's distance 9. Distance 9 patch. So the data qubits are kind of, like the measure qubits are the ones on these like long lines. And the data qubits are here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is a 9 by 9 patch, as you usually would. There are a few differences. You have filled in boundaries, so you have all the measured qubits instead of just alternating on the outside. That ends up not being fundamental, but it's something we're doing for convenience here. And we have a number of broken components. There's like a broken qubit here. There's a broken coupler here. Apologies if the red on red and blue is not super easy to see. And there's a few processing steps that end up not being fundamental, but I'll include here, where we're going to remove any qubit that has 2 broken couplers touching it at right angles, or a broken qubit and a broken coupler next to each other. So I'll track both of those as broken qubits as well. I'm then going to cut all the broken components broken qubits out of the chip. The broken couplers don't require me to cut any holes. I'll just have to measure things in weird ways to get around the broken 2-qubit gate. But if a qubit is missing, I need to avoid it. And the problem there is that if I remove a qubit from a weight 4 stabilizer, it's now weight 3, and it now anti-commutes with its neighbors. So those stabilizers are now demoted to gauge operators. So for those of you who are familiar with error correction, we're going to be using a subsystem approach here, which means that there are going to be Pauli operators I'm measuring, which do not have a well-defined eigenvalue, but do have a well-defined eigenvalue in conjunction with another Pauli operator that's being measured. So for example, in this case, this z operator, zzz, anti-commutes with this x operator. But the product of this one and this one does commute with this stabilizer, or this gauge operator. So when I measure this x-type gauge, I will scramble the eigenvalues of these two z operators, but I'll scramble them in a correlated way. So the product of the two will not be scrambled. However, the constituent eigenvalues might be. This will be important later, because I'll show you how we can sneak a few extra detectors in by being smart about how we do this. But we're going to have to now take these gauge operators, figure out all the products. In this case, it's not a very hard problem to do. But I've looked at this system at 10% dropout, things like that. And at that point, it starts being a bit of a tricky problem to figure it all out, because you're kind of looking at some nightmare mosaic on your chip. But in this case, the gauge operator is a group as you'd expect. And we then find logicals. They're basically the same ones you'd think about, but they look kind of different because the backing stabilizer group is different. But the point I want to make is that, as I said earlier, your logical operator is really a sheet in space-time. And so you're just propagating that same Pauli operator through a few C-naughts. In many cases, it's kind of trivial. Occasionally, in the mid-cycle, you'll have to there'll be a broken component here, so you end up walking your logical around. But there are many well-defined ways to find the logical operator of a stabilizer group. You can use any of them. They all apply here as well. So now that we have our background patch, we need to figure out how to fill this thing in with all these weird LUCI shapes I showed you to actually get a well-defined circuit. I'm going to do that by first, there's a bit of cropping happening. Sorry. I updated the figures, and I guess I didn't do a good job. What I'm going to do is I'm going to first start with a sort of default base LUCI diagram. So I won't prove this to you, but this diagram where I just have picked a random specific snake and then copied it everywhere back and forth and alternated, so this round and this round are the same right now. This actually corresponds to the regular surface code circuit up to two small modifications. One is that I have filled in these boundaries. So there are qubits that would normally not be present in the code that are sitting there kind of idle half the time. And the other thing is that because of this self-reversing structure of these mid-cycle constructions, the gate order reverses every other round. So if your normal C-naught layers are A, B, C, and D, every even-numbered round will be DCBA, and then A, B, C, D again. And that's because in reality, I'm thinking of this as CD measure reset DC, and then BA measure reset AB. That's kind of how LUCI is, how the LUCI structure is thinking about this, not how the regular surface code did. And this has interesting properties about hook errors and stuff, but it's basically equivalent. This is slightly better than the regular surface code. Whatever. I'm then going to cut out all of the things we cut out earlier, and I'm going to delete any shape that is impacted by that. So there used to be a U shape here. I removed it. Sometimes the U shapes work out with the broken coupler that happens to be there. In those cases, I'll leave them in. But otherwise, I'm just going to remove everything that has been impacted by the broken components in some negative way. And then I mentioned this note here. Sometimes, just due to the orientations of couplers, there might be a better base play to use than other times. For example, if you have a bunch of broken couplers that happen to be in exactly a 3-coupler orientation, you probably want to just pick the hex grid footprint that works for that and then just do that circuit instead. But I'm not going to talk about those optimizations right now. We then apply a 4-coloring to our checkerboard. So the reason for this is that these adjacent squares share qubits, so they're not mutually independent. But every red square here, for example, can be filled with whatever I need it to be filled with, and it won't collide with another red square. So I fill in all of the gaps that I have in my thing according to this 4-coloring. So I say, in this red round, every red square must be filled. So if we look at this square here, this particular square was empty. I've now filled it with this C shape to account for that broken coupler. This is going to lead to collisions. Now, I've added in extra shapes that aren't necessarily shapes that work with my previous object. And so I'm going to remove all the things that collide that are not colored. So I need to have this guy filled in this round. So I'm going to sacrifice this measurement instead. In a later round, down here, that measurement is important. And I'm going to skip the weird thing here that needs to be rotated. And this way, you can guarantee that you can, in 4 rounds, measure every single mid-cycle stabilizer you can get all your logicals and everything, you can protect your thing to full distance, or to whatever distance you achieve. And this gives you your final LUCI diagram. It's not optimal. I'll talk about improvements to it, but it actually turns out to be pretty good. When we were making this follow-up paper where we talked about all those optimization improvements, it's kind of hard to beat. There was a paper that came out, I'll talk about later, comparing against LUCI, where they filled out the full mid-cycle every time, but just rotated some columns, and that ends up having a dramatically negative impact on logical error rate. So this thing does pretty well, but you're going to see some big gaps in certain areas, and these will be areas that have detectors that are really high error rate and are possibly high valence in your detector graph. So they might be shortcuts or problem areas in your detector graph that'll often be where logical errors pass through. So this is sort of a final LUCI diagram. That's the process of making one. And I'm going to go over quickly sort of just the life cycle of a single detector, just so we can really understand how these modifications to the circuit and deformations have affected our final footprint. So I'll look at just this random 3x3 square of patches. And right here, I'm going to focus on this particular detector. So halfway through this round, I reset that qubit, and I used 2 CNOT layers to propagate it out. In the subsequent round, I'm not measuring this square. And due to these 2 broken couplers, I have done some weird fill-in of this particular board. So instead of measuring these 2 columns in the usual way, I'm now measuring just these 4 blue stabilizers, and I've rotated some things around. What that does is it propagates my weight 4 into this kind of fun mitten shape. And I now hit 2 measurements. Those measurements are tracked. I now reset them, propagate back, and then in the final round, I'm measuring this thing out again, and so it propagates from this weight 4 using CNOT layers back to weight 1, and then it's measured out. And the final detector is the bitwise parity of all the measurements that I hit along the way. So this measurement, and this final terminating measurement are all included, and that's my detector for that particular round. And so it's a pretty well-defined process. You can do this with just polypropagation. There's other simpler ways to do it, but you could imagine brute forcing this just through straight polypropagation. And if you do that for the full thing I showed you, this is the cross-section detector slice diagram you get. So I know that people not at Google are not as used to looking at these diagrams. We're trying to sell them as best we can, but it's slow going. The way that you look at these is these are the cross-sections of these detecting regions at every single point in time. So in the mid-cycle, it's well-defined because we're kind of using that as our handover point from one round to the next. And then this end cycle would normally look like a regular surface code. And you can see in areas that don't have much broken stuff that they sometimes do look like a normal surface code. But you can also see the other parts don't look so good. And the beauty of this is that we never need to deal with this. This works out. It's all automated. We never need to think about this code and its behavior. It's just sort of a place we pass through on the way back to a thing we understand and like to work with. And so it's just sort of there. The computer needs to think about it, but I don't. And so this is kind of the complexity that we're adding, but hopefully not too much because we don't need to face it ourselves. And the upside is that we get significantly better performance. So this plot is now a little bit outdated in that there are other improved things to compare against. But when I wrote this paper, the major sort of dropout methods used in the literature were the Strykis-Brown method and this auger/bandage method, this one being kind of the original. On the top here, I have heat maps of distance, and on the bottom, I have heat maps of logical error rate, where each of these heat maps individually has, on the x-axis, qubit dropout rate going from 0 to 2, and on the y-axis, coupler dropout rate from 0 to 2. So we can look at the distance plot first. We start with distance 15 footprints. So at 0 dropout, everything's distance 15. But then as the qubit and coupler dropout rates increase, we lose distance. Previous methods always lose 1 distance for data qubits and 2 distance for broken measure qubits. So a single broken measure qubit reduces your distance by 2 because it punctures a large hole in your surface code patch that leads to a large shortcut that your logical operators can take. And then broken couplers were handled by removing the adjacent broken data qubit. So they also lost 1 distance, which is why these look relatively symmetric in terms of x and y. In LUCI, you only lose distance for broken canonical data qubits. I have a backup slide that can explain why. So for measure qubits, you don't lose any distance at all. And for broken couplers, you don't lose any distance at all in isolation. When they're all next to each other, there are other cases. But this leads to this kind of asymmetry where you see this sort of vertical striping effect. Broken couplers don't matter that much, and so they don't impact distance. Broken qubits do, and so they do impact distance. And you can see distances are dramatically better across the board. At 1% dropout, We achieved 13.1% distance, and the best method previously achieved 9.1. So an increase in distance of 4 for the same grids. And you can see also it's much tighter. This is, I think, a big sell to experimentalists, that most, like, the bad chips aren't as bad anymore. So we hopefully wouldn't need to toss out as many chips to achieve some good performance. There's not some long tail. I then simulated this at 1% or 0.1% SI 1000 noise. And again, you see the same behavior. Things are much tighter for our method. And the penalty goes from being about a 600x increase in logical error rate for 1% dropout to about a 15x increase. Again, 15x is still bad. We don't want to increase our logical error by a factor of 15. But we'd much rather do that than 600. And so this means that some chips we probably couldn't use before, we now can. Yadi?
The circuits seem much longer though for measuring the stabilizer. How come the error rate doesn't get much worse?
So these are in memory, so we're not doing a stability experiment here. You would see a different result for stability because we're measuring some stabilizers less often. So the logical cycle time you can think of as being increased. All dropout methods, or all publicly known dropout methods, increase your cycle time by at least a factor of 2. LUCI's penalty is 4, although we have, talk about later about ways that we have to reduce that back to 2 as well. But the thing we've found is that essentially, in every case we've looked at, the improvement in logical error rate is worth the additional rounds you need to do, basically, assuming you have the dropouts. Again, relative to a no dropout case, you would rather not do this.
And how does the depth of this circuit relate to the dropout rate?
Essentially, it's going to be doubled, but it's still a 4 CNOT layer measure, reset 4 CNOT layers. It's just that you might need to do more than 1 round of those per thing. But for a single broken qubit, well, that's not exactly true, but generally speaking, assuming there's a good number of broken things around, you're going to need to do 4 rounds of CNOTs and measurements instead of 1 round for a dropout-free case, and instead of 2 rounds for all other previous dropout methods. Yeah. Daniel, and then I'll take it.
Okay, so when I learned lattice surgery in the subsystem language, the gauge operator can connect from the hole to the boundary. So here, why you're not reducing any distance?
So if you include the gauge operators and form a stabilizer, then you don't connect from the hole to the boundary. If you create an internal boundary, then you do. So you need to be careful how you multiply your gauge operators together to form stabilizers. In lattice surgery, the thing that we do have to worry about is that that's really when this 4x increase in the number of rounds we need to do really pays the penalty, is that we need to start making those crossbars taller. Otherwise, these gauge operators create a shortcut, essentially, because they're only measured every so often. So if you're worried about time-like errors, you only need to have d over 4 errors fail to get across the crossbar. So you need to increase the repetition round thing number of times. But yeah, you have to be careful about internal boundaries. Otherwise, I completely agree. That's why dropping a measure qubit is so painful in the previous method. Because to drop a measure qubit and just not measure that one stabilizer, you would introduce essentially a puncture, and you'd have an internal boundary that halves your distance. And so you instead need to remove those qubits as well, and that's when you get this huge, gaping hole in your code space.
Yeah, so can you go back to the previous slide? I just want to make sure I understand the details of this, just a couple quick. I think you already answered. So each of these 4 rows then are the 4 rounds.
Yes, and you would just do this, do 1, 2, 3, 4, 1, 2, 3, 4, and just.
Yeah, but aren't those just 3 CNOT gates for?
Each of these is 2 CNOT gates, a measure, a reset, and then 2 more CNOT gates to re-prepare back out. We're essentially just taking our usual picture and shifting it by half a phase. So it's the last 2 CNOTs from the previous round, the measure, reset, and the first 2 from the next round.
Oh, okay, and that's between.
That's what yeah.
Okay, so the other question was, why don't I see, a pattern? What's the pattern here?
Well, there's no pattern because if I copied this round back again here, then you would see the same thing here that you saw here. But I've only included the 4 unique rounds. So there's no, they don't look.
Each of these, if I want to get D rounds of syndromes, then.
I would just do 1, 2, 3, 4, 1, 2, 3, 4. Yeah.
Oh, sorry, but
sorry, time is going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And one of these is actually an idle round.
I thought it was the other way. Okay.
Yeah. Sorry, time's going across. And like this is the round that's described here, then this round describes this one, and so on.
But where do you get like one set of syndromes? Like, I normally think of d-squared syndrome somewhere.
Right, like you kind of get them along the way, honestly. So you're going to end up over the course of this 4 rounds measuring some of your end cycle stabilizers twice, but the slowest one will be measured once, essentially. That's what the problem. So that's why I'm saying like it's not exactly clear. You're not measuring every stabilizer once every 4 rounds. You're measuring many of them twice. And so for a single puncture, you probably don't need to repeat that many times. You just accept there's a weird time-like error that you're sensitive to. If you have a lot of dropouts, you probably start increasing the number of rounds. And this is what a stability experiment would tell us, which I won't. Okay. I don't have to.
So how much data do you have in this picture? I mean, how many rounds?
This is 4. Well, this is 4 LUCI rounds, which you can think of as 1 or 4 surface code rounds, depending on your dropout rate, essentially. I'm happy to talk more about this like specific distinction. But like, yeah, it's basically like I think your confusion is correct in that like there's a bit of ambiguous language here. Yeah. I think of this as a round, but this is not exactly a round in the traditional sense. In the interest of getting to the new stuff, is it okay if I table your question? All right. So anyway, logical error rates are better. Wonderful. I want to get into a few new things. So this is all from the original paper so far. I'm going to talk now about a few follow-up works that we've had that improve this system to some level. So the first one is an improvement to the way that we actually construct these mid-cycle gauge groups that we're working with. So previously, we thought that if you had a broken qubit and a broken coupler here, I would need to remove this qubit as well. And it turns out that's just not true. So this is the helpful thing about having talented coworkers. When Oscar Higgett joined our team, I gave him this paper to review because I was about to go out and I needed someone to review it. And as a new hire, he did not have any meetings on his calendar yet. And he came back and he was just like, you don't need to do this, right? And that was like just a significant improvement, but the paper's already written, so these things happen. And so it turns out that you can introduce a weight 1 gauge operator, which I thought would be kind of useless because this qubit isn't actually in the code. These now are demoted to gauge operators, which means that the stabilizer that they form doesn't have that qubit in it. But it turns out that that still has a significant improvement. So it makes your X-type superstabilizer go from this large weight 8 object to a weight 6. And in half of the cases, this means that we save the distance penalty. So we previously lose 1 distance in Z because there's now a shortcut here to here. And if you went the other direction, it would be the same shortcut. Now, in half the cases, we only lose distance in the X spaces. So the X distance is unaffected. The Z distance is improved in half the cases. And this ends up being actually pretty meaningful in a lot of cases. And this means that now we have dropout solutions for the hex grid surface code. So if you were interested in building a hex grid surface code, previously a single broken qubit kind of ruined everything because you have this cascade effect. Now we have a well-defined way to handle that. Nice. The other thing is improvements on how we actually generate these diagrams. So I showed you this deterministic kind of algorithmic way to do that. But it turns out that my intern from last summer was able to find a lot of really interesting things with ILP. So I'm not going to explain ILP too well because I don't really understand ILP too well. But essentially, it's an optimization framework where you go onto the internet, find a solver that someone else has written, or you could write yourself, but that's not what I'm doing. And then you create a cost model, essentially. There's a paper that came out around the same time as our paper came out by Wolonsky from Riverlane, where he actually extended a lot of LUCI ideas to color codes and BB codes, and then used ILP solvers to find these circuits. And he used a relatively simple cost model of just maximizing the number of measurements. We found that through some heavy research, we actually can do much better than that if we include a lot of other information. So we give it hard constraints, like avoiding gate collisions, measuring every stabilizer every 4 rounds at least, measuring gauges in a valid order so they don't get scrambled. But we also give it soft things like, oh, we want to get deterministic measurements. That's an additional detector. So you get a reward for every time you do that. You get a penalty every time you measure a poly less often, because that's going to create a big time-like thing. You get a penalty for stretching and detecting regions in bad ways. And you can give a lot of other information. And in doing all of this, you can actually improve logical error rates pretty substantially. One of the other things you can do is you can sneak in extra gauge measurements. So this is sort of a completely complicated aside, so I wanted to make sure I got to it with some time. In the usual picture, if I had this particular stabilizer group, so here time goes up, and the shapes I'm showing indicate which objects I'm measuring and then resetting in that round. I'll measure these X gauges. then I'll measure this X gauge, then I'll measure this Z gauge, and then these 3 Z gauges, X gauge and X gauges, and so on. And the detectors are going to be formed by these 4 measurements plus these 4 measurements, these 4 measurements plus the future ones, and so on. Does that make sense? Great. The interesting thing is that you can tell the ILP solver to try to sneak in extra measurements as long as they improve your gauge group. And what it sees is that you can actually add, for example, this square right here. This is also in that original paper, the second paper with Higgett et al. So you can sneak in this particular weight 4 here, this weight 4 here. Essentially, when I'm measuring this triangle, you can also sneak this X operator in as well, or this sort of opposite square. And what that does is it now makes your gauge detectors a bit more confusing. So now I'm going to compare, let's say I'll look at the red version. I'll compare this product of X gauges with the previous round. But when I'm comparing to the next round, I'll actually compare this set instead, where I'll use the newer weight 4 stabilizer, or gauge measurement. And because it's fresher, the detecting region is smaller, lower error rate, higher Fisher information, all nice things. So this already would be an improvement. But additionally, when I measured and reset this particular gauge, it now has a well-defined eigenvalue. Okay, give me 1 second, I'll hit it. And then after this round, it hasn't been scrambled, right? There's no X-type or Z-type measurement and anti-commutative that's been measured. So the stabilizer group at this point in time isn't just the whole product of all the 4 gauges. It's really the product of these 3 gauges and the product of this one individually. So when I measure this weight 4 again, I'm actually measuring a stabilizer of my instantaneous stabilizer group. So I get an additional detector as well, and I now have, maybe you can tell there's more of a nightmare on the right, which means more detectors are on the right. And this dramatically improves logical error as well. Ophelia, you had a question?
Yeah, what was it that meant in the original method those weren't included? Because I'd kind of assumed if they don't clash with what you're measuring, they'd have been there anyway.
Essentially, we didn't add things back in if we were trying to do sort of the traditional you measure X gauges and you measure Z gauges thing, because that's known to work kind of, and so I didn't want to mess with it. But the thing we're seeing here is that you can kind of use the gauge fixing ideas from the Higgett-Breukman paper from a few years back, or just this is kind of like shells, which is this thing that came out in this Strikus and Brown paper from a while back, where you basically the idea is that instead of measuring all the Z gauges, then all the X gauges, and all the Z gauges, it's better to measure the Z gauges, and then the Z gauges again, and then the X gauge and the X gauges again, because you get better stabilizer information out in the subsequent round, because you have all the gauges are actually stabilizers now, until you measure the opposite gauge, and then they're demoted back. And so you can get better information by doing this, and you can get significantly higher detector densities.
Okay, so is it that when you have the kind of 4 layers and the 4
Yeah, it's that 4 coloring thing kind of led us to
switch some of the order of
we
what that
basically
would
sneak
be?
additional things in. So the 4 coloring setup, so the first round is all X type, the second round is all X type. We might sneak in some Z type things as well now. But it's much easier to find by just telling the ILP solver to just get more things, please. So with that, we see some improvements in logical error rate, about a 20% improvement in logical error rate in this small instance that we really chewed on. These ILP solvers are slow. They're not slow, but they're not great. So we didn't do the same huge distances we otherwise would. But we see a 20% improvement in this I think distance 9 case. Yeah, Mingyu?
So when you add the gauge detectors, do you still do matching decoding?
Yeah, you can still. Yeah, this whole thing is matchable the whole time. Yeah, everything's matchable. We're all good. And then the last thing I want to mention in terms of last thing I want to mention in terms of improvement is our cost function. It's not perfect. We know it's pretty simple still, but we have this nice plot that shows that as time increases, you can look at the actual logical error rate of all the solutions it was finding, as well as the cost function over time, and you can see they're roughly aligned. So we think we're at least looking in the right direction. We're probably missing some specific details that could make logical error rate much tighter. And then there are still some non-monotonic behaviors, which means that there are things that we're rewarding that aren't good, or things that are not penalized than we should be. And so there's a lot of work that we still want to do here. And so that's what we'll be doing for the next few months, probably, at least partially. And then in conclusion, it's a flexible framework. It's really useful, yada, yada, yada. It can do all of the nice gates and things that regular surface codes can at the expense of it being more work to set up. But it's work that we have to do if we want to be able to work on these systems. And the thing that I wanted to sort of use to tie this into the work that we're doing here in this workshop is that error correction researchers tend to focus on codes and getting really low error rates to do things that are like, like Andrew's talk from just earlier, like these large numbers of gates. And maybe if we want to find a bridge, we want to find lower overhead things to do. And so I think that these 2+1 dimensional tiling type ideas and thinking about like building fault-tolerant processes that aren't codes might be a place where we can find really low overhead ways to slightly thicken our qubit wires and like, find gauges, find flags, find fault-tolerant bits of circuits without fully thinking about like, I'm going to design a new code. We probably have explored small codes pretty well. There probably isn't some magical distance 3 code for 10 qubits that gives us 5 logical qubits or something. I don't know. Maybe that particular set of numbers wasn't aggressive enough. But what there probably might be is some 3-dimensional tiling that's not periodic, that isn't well-behaved, isn't fun to think about, but does get us there. And so that's kind of maybe more of a challenge for error correction researchers than it is for NISQ researchers. But I think that's one place that our field could try to kind of lend a hand and sort of reach outwards with in terms of building things that are interesting to the NISQ audience. So yeah, thanks. This is all the papers. All the bold ones are the ones that I really stole from, and then this bottom one is this acid paper from Riverlane. Yeah, thanks.